Hi everybody, and welcome to my data structures and algorithms series. This series will replicate what a data structures and algorithms class would be when you are getting a computer science degree at a university. The only difference is you don't get a nice piece of paper at the end that tells you you got a grade, because I'm not grading any homework. But everything within this series you would learn at a university. This series is going to use C++ for examples. So if you are not familiar with C++, go check out my Introduction to C++ series so that you can get up to speed quickly and understand the example problems that are going to be shown throughout this series. With that, welcome to Data Structures and Algorithms, and let's get started. An essential aspect of data structures is algorithms. Data structures are implemented using algorithms, and an algorithm is a procedure that you can write as a function or a program. And an algorithm explicitly states how data will be manipulated. So when we create these algorithms, we need to be able to measure the algorithm, and that comes along with using computational and asymptotic complexity. Computational complexity measures how much effort is needed to apply an algorithm, basically saying how costly is the algorithm. And cost can be measured in different ways. There are two main complexity measures of efficiency. We have time complexity, which describes the amount of time an algorithm takes in terms of the amount of input. And then we have space complexity, which describes the amount of memory, space, an algorithm takes in terms of the amount of input. And for both of these measures, we're interested in the algorithm's asymptotic complexity. Asymptotic complexity asks, when the number of input items, or n, goes to infinity, what happens to the algorithm's performance? So let's look at a working example here. We have a function, which is n squared plus 100n plus log base 10 of n plus 1,000. As the value of n increases, we're going to actually see a shift in our importance. So in the very beginning, when n is equal to 1, the most important number, or basically the heaviest weight, is 1,000. 1,000 takes up 90.8% of the values in this function, because n squared is 1. 100 times n is 100, and log base 10 of n is 0. So the only value really that matters here is 1,000. When n becomes 10, then 100 times n and 1,000 are the most significant numbers, because 100 times 10 is 1,000, and then we have 1,000. When n becomes 100, n squared and 100 times n are the most significant values, because both of these values are 10,000. 1,000 now has become insignificant because it's slowly getting eclipsed by n squared and 100n. When n becomes 1,000, n squared is now pretty much the heaviest weight in this function. And that only becomes more obvious as n gets larger and larger. The only value that matters is n squared. When n becomes 10,000, n squared takes up 99% of the function's values. And when it becomes 100,000, it's 99.9% of the function's value. So what we're showing here is for the small values of n, 1,000 is the last term, basically, is the largest. But as n grows, the only item that it becomes significant in the function is n squared. That's what we're looking at when we are determining our computational and asymptotic complexities. So let's talk about Big O notation. Big O notation is one of the most commonly used notations for asymptotic complexity. It's the theoretical measure of execution of an algorithm, and this is usually described in the terms of memory or time. Big O notation expresses the runtime in terms of how quickly it grows relative to the input as our input gets arbitrarily large. That means we're looking at the upper bound of an algorithm. But let's break down what I just said there. When I say we're looking at how quickly runtimes grows, let's think about this. It's hard to pin down the exact runtime of an algorithm because it depends on the speed of the processor that is on the computer, what other programs are running as well on the computer, and a bunch of other different elements as well. So instead of talking about runtime directly, we use Big O notation to talk about how quickly runtime grows. When I said relative to the input, if we were measuring our runtime directly, we could express it in the terms of like the speed within seconds. But since we're measuring how quickly our runtime grows, we need to express our speed in a different term. So Big O notation, we're using the size of the input, which we're calling n. So we can say things like the function grows in the order the size of the input, which makes it a linear growth, or it orders in the size of like square of the input, which would be on squared. We say as the input gets arbitrarily large, our algorithm can have many steps that seem really expensive in the beginning, but those steps in the beginning are consistent or standard, and they'll slowly get eclipsed by the other steps as n gets larger. And for Big O analysis, we only care most about the stuff that grows fastest because of the input, and because everything else is obviously going to get shadowed or eclipsed when n gets very large. So the formal definition of Big O is f of n is the Big O, we say this here, this Big O of g of n if there exists a positive number c and n such that f of n is less than or equal to c times g of n for all of n greater than or equal to n. The values of c and n must be fixed for the function f, and they must not depend on n. Now let's look at our properties of Big O notation. First of all, Big O is transitive. That means that if f of n is equal to O of g of n, and g of n is equal to the Big O notation of h of n, then f of n equals the Big O of h of n. If f of n is the Big O of h of n, and g of n is the Big O of h of n, then f of n plus g of n is equal to the Big O of h of n. We're just talking about it in relative of the input. So you're saying f of n plus g of n, if they're both Big O of h of n, that's 2h of n, which at the end of the day, we drop our constant and we just say it's h of n. Next one is the function. A times n to the k is Big O n to the k for any a that's greater than 0. Again, kind of going back to this idea here, f of n plus g of n, which if those are both 2h of n, we're dropping that constant and we just say it's h of n. If a function is n to the k for its Big O notation, we can also say that it's n to the k plus j for its Big O notation, because we're talking about the upper bound. So basically anything that is larger than the Big O notation, the minimum Big O notation, also can be called the Big O notation, that Big O notation. Similarly, where we are with our exponents, we are the same with our base. So if something is log base a of n, then we just say that it's the big O of log base B of n. They're all the same in the properties of big O. Obviously in mathematics, not the case. So usually we don't even put a base when we're talking about our big O. We just say it's the big O of log n. The big O of a sum of a function is the big O of the largest function. So if I have something that is big O of n squared plus the big O of n, the final big O is O n squared. And finally, f of n is equal to the big O of g of n. This is true if the limit of f of n over g of n is a constant. So now that we know big O and we've learned the properties of big O, let's do a proof. We are going to prove n squared plus 3n plus 10 is the big O of n squared. So the typical way to do a proof for big O notation is to do a proof by induction. We are going to choose k is equal to 1. And what we need to do is to assume that n is greater than or equal to 1, and we need to derive a c so that f of n over g of n is less than or equal to constant times g of n over g of n, which basically is saying it's equal to c. This is implying that f of n is less than or equal to the constant times g of n. So in this case, we can say f of n will be our n squared plus 3 of n plus 10 over n squared has to be less than n squared plus 3n squared plus 10n squared all over n squared. And why is this? Because when we're saying that n is greater than or equal to 1, that also implies that 1 is less than or equal to n, and n is less than or equal to n squared, and n squared is less than or equal to n to the cube, and so on and so on and so on. And that's true, right? 1 is less than or equal to 1, and 1 is less than or equal to 1, and if we put it and we make n greater than 1, this is true as well. So we can now then say here that n squared plus 3 to the n, we have to handle this constant, so we make it n squared. And 10 then becomes 10 plus n squared. So n squared plus 3n squared plus 10n squared is 14n squared over n squared, which means we have 14. This is our constant. So we choose C. We choose C equal to 14. That is the constant that exists. Thus, n squared plus 3n plus 10 is n squared, because n squared plus 3n plus 10 is less than or equal to 14n squared. So we learned about big O notation, but big O notation only gives the upper bound of a function. So like the proof that we looked at before, we were looking at the upper bound. The upper bound was n squared. But in that same example, you could actually say big O n to the cube is also a big O, because it is also a upper bound, but it's not a very meaningful upper bound. So we need to also be able to describe a lower bound, which shows that like how the function always grows more slowly, and then a tight bound, which is a function that grows at about the same rate. So that brings us to two other notations, big omega and theta. So first, let's learn about big omega. Big omega is for lower bounds, very much the same of how big O is for upper bounds. When we say big omega, we are saying an algorithm takes at least a certain amount of time. The formal definition of big O is the function f of n is equal to the omega of g of n if there exist positive numbers c and n such that f of n is greater than or equal to c times g of n for all of our n's. This means that g is a lower bound for f after a certain value of n and without regard to multiplicative constants. So f will never go below g. So if the running time is omega f of n, we're saying that once n gets large enough, the running time is at least some constant times f of n. Then we have theta notation. Theta notation combines our upper bounds and lower bounds in order to determine a tight bound. The formal definition for theta is that f of n is equal to the theta g of n if there exist positive numbers of constant 1 and constant 2 and an n such that we have a constant times g of n, which is less than f of n, and then another constant times g of n, where f of n is less than that for all of our n. So in this case, when a particular running time is theta n, we're saying that once n gets large enough, the running time is at least within the constant, one constant times n and another constant times n, kind of creating these bounds that the function will stay in. Big omega and theta have similar properties. Big omega and theta are transitive, just like big O notation. The function a to n to the k is omega n to the k or theta n to the k for any a greater than 0, very much the same as our big O notation. Any k degree polynomial is omega n to the k or theta n to the k. Same rules exist for logs. The log a of n is equal to omega log n or our theta log n for all of our a's and b's. We don't really use the base to describe them. For big omega, different than our big O notation, the sum of the functions for big omega is the smallest function, not the largest function, because remember, we're talking about the lower bound. F of n is the big omega of g of n. This is true if if the limit of f of n over g of n is constant. And for f of n being the theta of g of n is true if the limit of f of n over g of n is a non-zero constant. Last two properties, we have n to the k is equal to the big O of 1 plus the epsilon to the n for any positive k and epsilon. This means that any polynomial is bound from above any exponential. So an algorithm that runs in polynomial time is eventually preferable to an algorithm that runs in exponential time. The log n of to the epsilon is equal to the big O of n to the k for any positive k and epsilon. This means a logarithm to any power grows more slowly than a polynomial. So an algorithm that runs in logarithm time is eventually preferable to an algorithm that runs in polynomial time. So we learned about big O notation, and we learned about big omega and theta notation. There are possible problems that can occur when you use only big O notation. If you understand it, is all the notation that we have learned serves the purpose of comparing the efficiency of algorithms that are designed to solve the same problem. If we use only big O notation, we can actually reject algorithms prematurely. So let's think about the fact that we could have two algorithms. We have one algorithm that takes 10 to the 10 n steps, and the big O notation for that is O to the n. We could also have another algorithm that takes 10 times n squared steps. So the big O notation for that is O(n) squared. On the surface, O(n) is better performing than O(n) squared. So using big O alone, we actually will reject this second algorithm because it grows too fast. But that's only true if n is less than 10 to the 9. And it's pretty often that n is going to be smaller than 10 to the 9. So really, the second algorithm will be faster than the first algorithm. So in these cases, we have to consider other factors in our analysis, and that is where we pull in something called double O notation. This has been proposed so that we can say that the constant is too large. So in this case, we would say that f is the double O of g of n if the big O of g of n and a constant c is too large to be useful. So basically we're saying 10 to the 10 n is big O of g of n. So let's look at examples of different types of complexities. Algorithms can be classified by their time and space complexity, and the class of an algorithm is the name used to refer to its big O notation. And it's a more convenient way to describe its behavior. So, for example, a linear function is big O of n. It's the time is increased in direct proportion to the amount of data processed. We have other types of ways to see this growth. And this is kind of useful when you want to look at and say why something is better or worse. So, you have O(n) is our linear. Here's a constant at 1. The logarithmic, so Lg of n, and then n times Lg of n squared, and then n to the 3. So you can see how the growth rate is significantly quicker in n cubed versus n versus log n. So let's look at some examples. In our first example, we have a function print the first item. So we're taking in a vector of any number size items, and we're going to print out only the first item. This is a constant task. It only happens once. This is just a constant. It happens a set number of times. So we can say that this function has the big O of 1. It runs in constant time. In this example, we are printing all items. So we're intaking, again, a vector of items, and it can be any size. So we're saying for int of 0, I being less than the item size, I++, we're just iterating through the entire list of items and outprinting them. This, because it can have any amount of time, we can say that this little area here takes n being the size of the array. So in this case, we can say that this is the big O of n. It runs in linear time. So in this example, we are doing a print all of all possible ordered pairs. We're taking in our vector array, and we're iterating through our array. Here, we already established this is going to n times. This, again, is going through our array another n times. But this n is inside this loop. So we do a loop for n times, and then for each one of those, we do another loop. So this is n times n, or big O n squared. For our next example, we are printing all items twice. So we're iterating through our array one time and then another time. So this is n, and then we're iterating again through n. So this is actually n plus n, or 2n. But remember from our big O properties that we can drop our constant, so this is just the big O of n. So now let's look at this example. This is print the first half, then meow 100 times. So we're taking in our array of items, and in this case, we are printing out the first half of items. So int I equaling 0, and then the size of our array list divided by 2. This is then n divided by 2. And then we print out meow for a constant amount of time, always occurring 100 times. So this happens 100 times. So this is n divided by 2 plus 100. The big O of this is O n, because really this here is 1/2 times n. We can drop our constant, and then it doesn't matter this constant as well, so we can remove that, and that makes us have the big O of n. In this example, we're printing all items and then all pairs. So getting in again our vector. So here we loop through every single item in our array, that's n, plus we do our ordered pairs. So the first loop goes through n times, but then there's an inner loop that goes through n times. So overall this makes it n squared. So going by our rules for big O notation, we go with the highest polynomial. So the big O for this is O n squared. Because this was n plus n squared, the highest polynomial is our big O. Now, here is a fun example. This is the Fibonacci sequence, and it's a recursive function. If you're not familiar with how recursion works, you can go back to my introduction to object-oriented programming for C++. You can look through that and you can learn a little bit about recursion. But recursive functions basically are calling the function within the stack here. So in this case, we have the Fibonacci sequence. The Fibonacci sequence, if you're not familiar with it, it goes 1, 1, 2, 3, 5, 8, 13, and so on and so on. What it is it's adding the previous number. So actually there's 0 here. So 0, 1, right? So 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 5 is 13. For our Fibonacci sequence, we're writing the recursive function this way, that if the number is less than 1, we're going to return the number. If it's less than or equal to 1. So if it's 0, we're going to return 0. If it's 1, return 1. Otherwise, we're going to return the Fibonacci sequence. So let's look at this if we put in 4. If we put in 4, 4 is not less than or equal to the number 1. So it's going to return, it's going to actually call 4 minus 2, which means it's going to call 2, and it's going to call 4 minus 1, which is 3. So 2 is going to come in. 2 is not less than or equal to 1. So then it's going to call the Fibonacci sequence for 0, and the Fibonacci sequence for 1. And then 3 is going to call the Fibonacci sequence for 1, and it's going to call the Fibonacci sequence for 2. So if you're looking at this, each call for the Fibonacci sequence creates a binary tree of calls out 2 times here. You'll learn more about binary trees later on in this series. But right now, just think about the fact that it has 2 children. So when we call 4, it spins off 2 children, which is 2, and 3, which then spins off its own 2 children. Then see here, this one spins off its own 2 children. So if we see that, we got a possibility of 2 at every single one of these tiers, and it can be called n times. So it's actually 2 to the n. So there's a big O notation of 2 to the n. So let's look at one more example. This example is called print meow. So in this case, we're taking print meow and we're taking in an x, and we're going to print out it for, we iterate through I equaling 0, I is less than x, and then I gets incremented where it doubles. This is demonstrating an algorithm that runs in log base time, because this is going by the log base 2 of x, or n, log base 2 of n, because in this case it's getting multiplied by the number 2. So it goes from 1 to 2 to 4 to 8 to 16, so on and so forth. That's the log base 2 of n. So we can say the big O notation for this is O log n. We have completed learning the initial part of our complexity analysis. We learned about Big O, Big Omega, and Theta, and we also learned how to, 1, prove Big O notation, and we had saw some working examples of Big O notation in actual functions. In my next video, I'm going to talk about best, average, and worst case. This is how we can get a handle of complexity for more complicated algorithms. And we'll also learn a little bit about NP completeness and why that all matters. So if you liked what you have seen so far and you want to get notified more for further data structure and algorithm videos, please click the subscribe button so that you can get notified when the next video comes out. Until then, happy learning.